I'm going to adjust things. So I'm just going to let you know, I thought that I had this all typed up, but I don't. So I'm adjusting as we speak. Here we go. So we are, I'm just making sure everybody's very clear on this, having a lab this Wednesday, correct?
Tomorrow, yeah. Okay.
Yes, tomorrow.
Okay.
We agreed on that before spring break. You all told me you could be here, so please don't tell me you can't, because we have to get it done. Okay, so tomorrow, that's this day, I will be here by 3:30. I have to come back from East, because that's where my meeting is at. So we will be doing the RC circuits lab and information, okay? It's not hard stuff. I spent a little time over break just kind of getting my head around it, and it should be fine. But I will tell you that on the free response questions, when I was looking for circuits questions for the test, every single circuits question for the free response section has RC circuits on it. So it would be good to know it, okay? And I don't mean that in a threatening way, just in a, every single one has that. So we need to make sure we know that. So that's going to happen tomorrow on the 25th. I am adjusting what I'm doing today, so we are not going to do this content. Oops, let me change this. This content right here, we're going to cover when we do the lab on the 1st, because I think it fits better there and it makes more sense to. Okay? So I'm actually going to start chapter 33 today. I'm going to start the induced current stuff today.
Wait, so tomorrow's 3:30 to 5:30?
3:30 to 5:30.
Okay.
Okay. I am still working on writing the lab, so I don't know exactly, but let's plan on the 2 hours, and if we don't need it all, that's fabulous, and if we do, then we'll use it, because it is important stuff, so I want to make sure that you understand it. Does that make sense to everybody? Okay.
Wait, can I please just get a note to give my track coach?
Remind me at the end of class, and absolutely, okay. I will do that. Yep.
What time is it? It's the lab.
3:35.
Just double checking, you know.
3:30 to 5:30. That's when I'll be here.
I don't want to be late.
3:30 to 5:30. So today we're going to start chapter 33. I'm hoping to push this earlier. Just the more that we can push up, the better. But I'll kind of keep you posted on how that, where that test is falling. Does that make sense? Okay. Questions about that at all? So these are going to be stepped up a day, depending on how far we get today. We'll just kind of play it by ear. Fair enough? I do have tests to give back to you at some point. We'll just get those back as soon as we can. I know you've been waiting feverishly for those. So, questions before we begin with content?
So what we were supposed to do today is during the lab next time, like next week?
The forces, this one section makes more sense to just do when we do this lab.
Oh, okay.
Yeah. So I'll talk to you for 15 minutes about what it is, and it will fit in right here with this lab. We didn't need a full day for it, so let's not spend a day on it. This 3210 stuff is interesting. It answers a lot of the questions that people have, just kind of like about general magnetism, how magnets work, but it's not part of the content that's required for the course. I would recommend reading it just because it's interesting, but it's not something I'm going to test you over. Okay? All right. Now, before we actually jump in and get started on chapter 33, there were a couple things from magnetic forces and current carrying wires from the last time that I wanted to do. So would you pull out your notes from last time? I know it's been a while since I've seen you. I know it's been a while since we've done some good physics, so I want to make sure that your heads are there, heads are with me here before we jump in. So last time we were together, we were talking about this idea of a magnetic force on a current carrying wire. We talked about the fact that there's a magnetic force that exists anytime you have a charged particle that is what? Moving. It has to be moving. If it's not moving, there is no force, right? So if you have a charged particle that is moving in a magnetic field, it will feel a force. The direction of that force can be found with the right-hand rule. So none of you broke your right hands over spring break. Yay for you. Good job. Velocity, B field, force. Right? We talked about that. We used the right-hand rule to find the direction. And the magnitude was QV cross B, or QVB sine theta. Hopefully then we convinced you that if you have a current carrying wire, that's just a bunch of charged particles that are moving. Oh, if they're moving in a magnetic field, then that current carrying wire is going to feel a force. Okay? And if instead of having one current carrying wire, you have two, then each current carrying wire is going to create a magnetic field, and the other current carrying wire is going to feel a force because of that magnetic field that was created. Does that make sense? So the pink wire is going to feel a force from the magnetic field that the green wire creates, and vice versa. This is sounding kind of familiar. I know, again, it's been a little while. We just need to jump back in here so we have this in our head. We calculated the force and found, oh my gosh, that the force of 2 on 1 and the force of 1 on 2 are
Equal.
the same in magnitude, opposite in direction. That is just Newton's third law. It's just another example of Newton's third law.
If I1 and I2 are the same.
Nope, don't have to be. They don't have to be because the B field that's created here, so the B field that's created by B2 has I2 in it. So you're going to have I1L times mu naught I2 over 2D. Here you're going to have the same thing except your I's are switched. But it's
multiplication.
Yeah, it's just multiplication. Yay! Computer properties of multiplication. Is that okay? So I think, if I'm remembering correctly, we got there, but then we didn't get any practice. Is that correct? Does that sound right to you?
Yeah.
Yes.
Okay, so I want to give you the practice questions. I didn't want to just throw them at you because it seemed kind of cruel without having talked about that. There are actually 4 questions on here, but you're only going to work on 2 of them. The 2 that I'm going to have you work on are 2010 and 2011, and I did print them off for you so you have access to them, but they're up here as well, so we can kind of talk through them. So I'll give you a couple minutes to work on these, to think through them. I'm not intending that this be like a super long experience, but I do want you to work through them. So I'll give you a few minutes to just take a look, to work.
Is there a text,
Obviously, ask me questions if you want.
is there a textbook anywhere?
A textbook. So for 2010, let's start with that one. I'm just going to move it down so I can write above it. Maybe. There we go. So the 2 wires are 2 meters long. The cords are 3 millimeters apart and carry a current of 8 amps. So you want to know the force. So the force of 2 on 1 will be the same as the force of 1 on 2, right? Okay. And we came up with that relationship last time we were together. And let's build it again if we need to here. So the force is going to be I L cross B, right? Yeah. And so that's just going to be I LB times the sine of theta, but we know that the sine is going to be 1. Is that okay? Because the B field's going to be going. Are you guys okay with that or no? Talk to me. Yeah? Because the B field's good. So if you have 2 wires going like this, the B field's going into the page here, and so that means you've got a B field going into the page and the current's going this way. So that means that you're going to feel a force that's at a 90-degree angle, right?
Yeah.
Okay. So the B field is perpendicular to the current. So if they are, then we can just say that's I times L times B. And that's going to be the force, but then we need to find the magnetic field. And the magnetic field that 2 is created, okay, how do you quantify that?
I2 mu over 2 pi.
Say that again.
I2 or mu I2 over 2 pi.
Oops, that's ugly. Let me try it again. So mu naught times I over 2 pi d. Okay, where if we're going to talk about this very literally, let's do it real quick. So this is the force of 2 on 1. So this is going to be the current of which one? 1, right? And we know that it doesn't really matter, but let's write it down anyway. And this is going to be the current of 2. So we just need to plug numbers in, I think, don't we?
Yep.
We know the length. We know the distance between them. We know the current. And it's going to be the same current in each one because you've got 8 amps going one way and 8 amps going the other way.
Yeah.
Okay? So the force that you get is how big?
0.0853.
So like 8.5 times 10 to the negative third or something?
I don't know. I didn't guess what it is.
And then direction.
Yeah, but a huge factor of 10.
What happened with your factors of 10?
I'm like
Off by a few?
quite a bit. I don't know what I did.
You messed up mu naught.
What's U naught is?
7.
10 to the negative 7?
That's why. Dang it, AJ.
Yeah, come on.
Every time.
I've been out for 2 weeks.
Oh.
That's not an excuse.
It is an excuse.
It is not an excuse.
Is it going to be a repulsive force or an attractive force? Attractive? Says Nathan. Do we believe him? I don't know. I'm asking. Let's figure it out. I wouldn't trust anybody, right? Never trust anybody. Don't. If we're talking about, let's talk about this wire, the one on the left. We're talking about the B field that comes from the one on the right. So use your right hand. Where's the B field going to be going? Over here on the left-hand side of this wire. Where's it going to be going? Into the page. Would you agree? B field going into the page over here. So you've got B field going this way. Right? That's what it's feeling. And then we're just going to use the right-hand rule. So we've got the velocity or the currents going up. B field's going into the page. So this wire here is going to feel a force where? Away from. Right? What about for this wire?
It's just going to be opposite.
Is it the same deal? I don't know. Are you convinced of that? Do you want to talk that through? Newton says so it has to be. It will be repulsive.
So F of 2 on 1, you use the velocity of the first wire then?
The current.
The current, yeah, sorry.
Yeah.
Okay.
So the current, the B field, and then the force.
Okay.
Yeah.
Does it say they're opposite? The currents go in opposite directions anywhere?
It's kind of implied in that it says that you've got an appliance cord. So if you look at like a lamp switch, right, or a lamp thing, it's got the two things,
Yeah.
right? And so in order for it to make sense, one's got to be going in and the other's got to be going out.
Okay.
Yeah. All right. Have you tried the second one yet?
No.
All right. Give the second one a try if you haven't done that yet.
I think that's wrong, dude.
Yeah.
So I think you're just off by an order of magnitude. Did you listen to AJ again?
No.
Did you do 7 or negative 7?
I did negative 7.
Okay. So let's go through number 11 real quick, just so that we make sure that we get it here.
Oh, wait, hold up.
Oh, she lost.
Yeah, that's what I did. Yeah, I got it.
Lost some factors of 10.
Yeah, no, I forgot that grams are not kilograms.
Yeah, these things do make a difference. What are we getting for I2?
14.7.
14.7 amps.
Yeah.
Cool.
And then in the direction they should.
In the direction that they show. So that part's done.
Yeah, I just saying this is a general comment. Like if asked for current, you have to specify which direction.
So I would say to cover your bases, I would, just so that do you know what I'm saying? If it has a picture like this and it shows it in the direction, then probably that's not something that they're going to require of you. But it's better to put it and not need it than vice versa. Yeah. I would always include both magnitude and direction if you have something that has that direction. Okay. So we feeling okay with this?
Yeah.
Okay. A lot of this is just applying it to different situations. Once you know how to find that field and that force. Okay? Anything else on this before we move on to the next realm of the world? Okay. Did you have a question, Pratik?
No, it's
Okay. I do want to remind you, just because I noticed it on the board and I don't want to forget, the last day to order AP exams, like for real, the last day is next Wednesday, April 1st. If you have not yet ordered your AP exams for this class or other classes, you need to do that by Wednesday. I would strongly encourage you to take both the AP Mechanics C and the AP E&M C exams. I think that you will be ready, okay? We will have covered all of the content, I promise. We will have a little time to review both things, so I would encourage you to take both. If you're not sure or whatever, generally people would take mechanics and not E&M and not the other way around, but you can do whatever you want. I can't force you to do anything. I would encourage you to take both, though. Okay, do you guys have any questions about any of
I
that?
feel like it's just a scheme to get more money.
It really is though. Like it's kind of ridiculous.
Here's my take on it.
They're both $91.
I think that's totally ridiculous. I will agree with that. Here's what I would say about the credit not credit thing. Okay? At this point, in a month and a half or whatever it'll be, you will be ready to take these exams. You will know the stuff. Okay? Who knows what's going to happen in a year or in 2 years or whatever. It's better to have the credit and not need it than to get somewhere, wherever that is, and then decide to transfer schools, and then, oh my gosh, you could have gotten through so much faster, right? Whether you're doing something in the sciences, or whether when you're at whatever fancy pants school it is, you find that instead of doing a science, you have a very, very strong passion for whatever. I mean, pick something that has nothing to do with science. Getting these credits and getting them done, it's going to be better for you. That's what I would recommend. I do agree that College Board is kind of sucking your money, but it's still cheaper to pay whatever it is per test here than to pay that. I mean, if you're going to look at it from a financial perspective, it is cheaper than paying to take the class again. So, can I be done with my spiel? If you have questions or you want more information, let me know. All right. Here we go.
Wait, do you know if that's an 8 or B? Because I know that's ITBS, but do you know if that's an 8 or a B day?
Because it's the weird ITBS day,
Or is it like technically
I think they are making
it's a
it,
no day?
and it's yellow on our calendar, so I think a B day, but I don't know.
Gabe's gonna be the only one here.
You know. No, Gabe and Logan. We'll have a good time. All right.
Wait, do I still?
Yeah,
Do we still
I
have to
know.
be here then?
According to
Do I have to take it?
According to the district, yes. But if your mom happened to call and say that you were not coming, I wouldn't cry except that I am running.
Okay. Will you still be covered?
I will not
I
cover
guess
new
if it's a B
material.
day, then.
Well, one of them is an A, one of them is a B. All right, guys, let's get back focused because we don't have a lot of time. Shh. Let's stay focused. Next Wednesday is not a normal school day. Yes, we know that that's ITBS day, or whatever you want to call it day. Iowa testing day, okay? So we do not have class. Like there are not classes here. You out-of-district people can do whatever you need to do, okay? But know that if you don't show up and nobody calls you in, then you are counted absent, okay? If the phone call is made, then it's not a big deal. That's all I'm saying. I'm not going to cover new material that day, though. Okay, chapter 33. Here we go. This might be one of my favorite chapters. I will tell you that this content is stuff that many people find to be kind of perplexing, but I'm not really sure why. It's not intuitive. Perhaps that's why. I'm going to introduce it today with 3 different experiments. Okay, we're going to do one of them in class, and then the other 2 we're going to talk about. But we're going to make some observations and try and draw some conclusions from it. So why don't you meet me right next to Brian there? We're going to take a look at So we have just so we don't forget this, we have a solenoid connected to a galvanometer. And to remind us, a galvanometer is just going to measure current. And what are you observing? What did you see?
Changed current. There was current when the magnet was moving.
So the current, oops, I forgot the L, didn't I? Galvanometer. There you go. Tell me again, Gabe, what you said?
There was a current when the magnet was moving in the solenoid.
So current, what's the verb?
Create.
Induced.
Created is the simple way. Induced is the I think I know what I'm talking about sort of way. It is actually the right word. Induced just is a fancy way to say created. So the current is created or induced when what?
When the magnet was moving in the solenoid.
When the magnet
Perpendicular mainly is when you're stirring it, it didn't really do it.
moving what?
On purpose.
Okay, what else did you observe? Somebody else. We did observe that. I would agree.
Directions.
North pole, where the magnetic poles.
John, speak. What?
John?
Or not John. I'm sorry, Andrew. Brain lapse there. I apologize. Andrew, what were you saying?
When the North Pole enters first, it creates a. It's like
Maybe make a more general statement than which way it goes.
different poles create different. None of my best.
All right, somebody tell me what I should write down.
Like about the poles and how that affected the current.
Yeah, but I want to know more detail. Like, just tell me in kind of a general way. Jack, what did you observe? What did you see?
That the needle was, in the galvanometer was deflected a different way depending on which pole was going into the solenoid first.
Yeah, the needle was deflected in a given direction, maybe? Depending on, what'd you say, which pole was?
Through the solenoid first.
Even at first, maybe, which is in the direction of the movement.
I think that's okay for now. Yeah.
Alright. And then should we also mention that it was an alternating current? That
Okay.
As the needle oscillated.
So,
Just the same.
as the opposite pole passed through the solenoid, what happened to the current?
So it was alternating. It oscillated.
It didn't oscillate back and forth and back and forth and back and forth, though, really, did it? Or did it just like go one way and then the other way?
It only really, yeah, it went one way and then the other way.
Okay. So, change direction, maybe?
What's the sign on B for north and south?
I don't understand what you're asking me.
Like is north, like if your current, which way is north pole?
B field lines go out of north into south,
Okay.
just like they go out of positive and into negative. It's the same principle. Okay.
So out of the page is north?
I wouldn't call it that. I wouldn't use those words because that gets confusing. When you have a current carrying wire, you don't have a north pole and a south pole. You just have a magnetic field that's in a circle, right?
So
I would only use the north pole, south pole thing if you're talking about a permanent magnet. If you're talking about an electromagnet that's actually created electric field or magnetic field lines so that it looks like that.
So if you have a coil, I'll figure it out.
Okay. We'll get there. I think you're trying to go too far, and we've got a lot of this stuff to do still.
Yeah.
Okay? All right. Questions about this? Because I'm going to move on to number 2. Experiment number 1 is done. All right. Michael Faraday, he was pretty famous. He's the one that figured all this stuff out. The law that we're going to talk about at the end of this conversation is named after him. And this is the experiment that he did. Okay? Maybe not with a fancy ammeter like that, because he lived a long time ago, but it's the same idea. So let me tell you the story. You may want to draw this picture or something similar to it just so you kind of have a sense of what's going on. I'll give you, I don't know, 45 seconds to draw. So go ahead and draw a picture real quick. And then I'll tell you the story that happens here. so that we can maybe get some sort of concept of what's going on. So you've got a battery. You can draw it like a little battery too. You've got a ring of iron. You've got 2 loops of wire that are connected to that iron ring. They're just wrapped around it. They're not electrically connected to it. They're insulated wires. The second coil is hooked only to an ammeter. A galvanometer is a simple way to say that as well. So here's the story. This is what's happening. There are kind of 5 different cases that we can talk about. So let's start at the beginning. Case 1 is exactly what we have drawn here. The switch is open. What do you notice about the current that's measured on the ammeter? 0. That makes sense, right? There's no reason it's measuring the current in this loop. This is not hooked to anything. Like, why would there be a current? There is no current. Doesn't make any sense that there would be. So in 1, the switch is open. And the current equals 0. Well, that was fun. Step 2 makes it a little bit more interesting. Step 2, the switch closes. While the switch closes, the current is measured to be greater than 0. Just for a moment. That's kind of weird. It's measuring a current. There's no battery. There's no reason that there should be current running through this thing. Step 3, well, after the switch closes, then the switch is closed. And at that point, there's no current anymore. So that's kind of boring. Jack, do you want to make a prediction? What's going to happen next in the story? I was going to open the switch, yeah. And Brian, do you want to make a prediction about what's going to happen?
No.
Okay, that's why I asked the question the way I did. It's totally fine.
Is that as the switch closes, and that's when it is closed?
Yep.
Oh.
Yep.
So wait, I'll predict while it's being open, I will be less than 0.
You are correct. For a long time?
No.
No.
But it was not actually.
What's that?
You can't have a current with less than 0, right?
Yeah, it's just current going the other direction.
Boom.
You did it when we did on the galvanometer, right? That's exactly what we saw. And then
He was convinced it was magic.
that it was magic?
Yeah, it's all
Yeah,
magic.
well, some people you just can't get through to them. And then when the switch is open,
That's just number 1.
right. Then it is just number 1. There is no current. Okay, so this is weird. In order to measure a current in a wire, what do you have to have? In order to measure, you have to have an ammeter. In order to have current in a wire, what do you have to have?
Magnetic.
You have flow of electrons.
You have to have a flow of electrons, right? If you have a flow of electrons, how do you get a flow of electrons?
Potential field.
The what?
Potential difference.
A potential difference. Where does the potential difference, where do you get a potential difference? How do you get a potential difference? A battery, right? Or an outlet, right? That's how you get a potential difference. We're measuring a current in here charged particles to move, and my goodness, you're measuring a current, but there is no battery or outlet or any reason that there's an electric field that's being created in here. But something is happening. What's happening? AJ, what do you think?
When you close the switch, the electric field in the primary coil pushes all the electrons that are just bouncing around inside the iron loop.
No.
No?
This is not electrically connected to the
Right,
iron.
I know, the magnetic field.
You didn't say magnetic field.
Did I say electric field?
You did.
Oh, I didn't mean to say electric field. I meant to say magnetic
That's an
field.
F.
Okay, so let's back up and start over, because I think you're kind of there, but kind of you not so much. Keep talking.
So the magnetic field in the primary coil.
Okay, so let's pause there. Is there a magnetic field created in the primary coil?
Switch close.
Yes.
Yes. Do we agree? Magnetic field, why? Because there's a current, right? So you've got a current going in this direction, so you're going to have a magnetic field that's created inside this coil. I'm good with that. Now keep talking.
And then since the electrons in the iron ring are moving, they experience a force.
There's no current in the iron.
Does it have anything to
But
do with
then-
something we haven't learned yet?
No.
What are you getting to?
No. I mean, I'm covering something that is new, right? But this part isn't new. What is iron? Iron is a really good what?
Conductor.
Well, yeah, but that's not
Magnet.
It's a magnet, right? Ferromagnet. Ferro comes from iron, right? So iron is something that is very, very easily
Magnetized.
magnetized. So if you have a magnetic field that's been created in this coil, then that's going to create a magnetic field in this iron. Are you with me there?
Which creates a magnetic field.
Which is going to create a magnetic field in
The other coil.
this coil,
Well, then.
which something what?
It's a solenoid.
What's that?
It's like the solenoid.
This part is exactly like the solenoid, right? I've got a magnet that's going through.
Yes. And then, but it stops.
Okay, and that's what my next question was. So Andrew, tell me what you just said.
I was thinking maybe maybe the magnetic field basically a period of time like induced, so like travels around the ring and then moves.
The very finite amount of time.
Other than that,
Why? Okay, so we made it to here, right? So you close the switch, we create a magnetic field inside this loop, which makes a magnetic field in the iron, which makes a magnetic field here, which for some reason makes something happen like it did in the solenoid, right? So then this part is like the solenoid. Now, that makes everything happy, but then what about in step 3? The switch is closed. It remains closed for a while. And what's the current measured?
Isn't that like if you just had the magnet in there and it wasn't moving? It's kind of
So
Yes.
in like yeah.
the magnetic field is changing, and that's what causes it.
That's the key here. Yeah. Yeah. So really the thing that's going to induce current, and we actually say, because we believe that a current has to come from some sort of potential difference, that an induced current is caused by an induced voltage or an induced EMF. We've talked about EMF before, right? The electromotive force, which for our intents and purposes is the same as voltage. We're saying that must only happen if what? Jack, you said it a second ago.
The magnetic field is changing.
If the magnetic field is changing. Does that jive with what we had for the other stuff? For steps 3, 4, and 5? So step 3, there's no current. Step 4, the switch is opening, and there is a current. The B field's changing. Why is it different from the one before? From step 2. Yeah, the B field is changing now from, oh, so I had B field this way to what's the B field here now when it's open? Careful. When I open this,
Does nothing, right?
yeah, the magnetic field here is 0, which means there's a change in magnetic field from something to nothing. And that's going to cause a change in the, or it's going to cause a current. And then when it's open, then again it's 0. Is that okay? Okay. Weird, maybe, but it's kind of fitting okay so far. Okay. Totally separate story. Here we go. This is the one that I think has the funniest name of everything that we do. It's called motional EMF. When I first heard this, I thought that I had misheard the very beginning and it was emotional EMF.
Yeah, that's what I saw.
Right? This is not very physicsy. Crying EMF. What is that? I don't know. No. Motional. Motional just means that it's EMF that comes from motion. So here's the setup. We've got a magnetic field. Does that surprise you? Probably not. I'm going to set that magnetic field into the page. So go ahead and draw yourself a little magnetic field. It's a uniform magnetic field into the page. And in that magnetic field, I'm going to take a bar of metal. Now, to be clear, I'm going to draw a bar of metal here. It is not a magnet. It is just a piece of conductive metal. That's it. Okay? So here is my bar of metal. And I'm going to take that bar of metal and I'm going to move it with a constant velocity in that direction. So maybe it's on a frictionless surface or something like that. And so I just give it a push and then it's going to move at a constant velocity, right? Like no big deal. Is that okay? Okay, because then its net force is 0, so life is good. So I got this moving bar, okay, in this magnetic field. What's going to happen in that metal bar as it moves through the magnetic field?
It'll experience a force.
What will? The bar? Why? I don't know. What is metal made of?
Metal.
Atoms, right? What are atoms made of? Protons, electrons, and neutrons. We don't really care about the neutrons because they're neutral, so we've got charged particles, right? You've got charged particles that are moving through a magnetic field. Those charged particles are going to feel a what? Force. So get your right hands out. Let's do it. So those charged particles, let's talk about the positive ones because they're easiest to deal with, are moving in this direction. The magnetic field is going which way? Into the page. So the positively charged particles are going to feel a force where? Up. Are the positively charged particles going to move?
No.
No. The chemists are going to tell you absolutely not. Why would they move, right? They're in the nucleus of an atom. Like, that's big. But what will move? The electrons. And the reason we need a metal is that we need those electrons to be able to move easily, right? So what's going to happen when you have this is that you've got this metal bar that's moving, and as a result, the charges are going to separate. Okay? So you're going to get a whole bunch of positive charge up here. And to be clear, it's not because the positive charges are moving, it's because the negative charges are leaving. And so you've got a bunch of negative charge down here. Okay? So the charges separate. Are they going to continue separating forever?
No.
Like, oh my gosh, I've got a bulge of electrons here and like a whole lack of electrons there. No. Why not?
Because it'll be there reach a point where the force of the electrons pushing on each other is equal to the force of the magnets pushing the electrons down.
There's also the protons on top,
Pulling the electrons up.
which are
Yeah,
attracting the
attraction.
Yeah, so that force is pretty small because the distance is pretty big, right? But if I've got a bunch of electrons hanging out here, do they really want to hang out together?
No.
Not so much. So at some point we're going to reach equilibrium. And we're going to reach it exactly when Brian said, right? When the electric force that those electrons feel is equal to the magnetic force, equal in magnitude, opposite in direction. Is that a Newton's third law pair? No, I'm just making sure, right? Just because they're equal and opposite doesn't mean they're third law pair. Just making sure. Okay. We can quantify the electric force as the charge times some sort of potential difference, right? We get a potential difference when we separate charges. And that thing has to be equal to QVB times the sine of theta. But the sine of theta is going to be equal to 1. So I'm going to leave that out. So we're going to reach an equilibrium when the potential difference, because of that separation of charges, is equal to the velocity of the bar times the magnetic field. Okay? You do have to be careful because you've got a little v and a big V in this problem, right? So make sure that you're paying attention to that and writing things clearly. Okay? Oh wait, that's not, I wrote that wrong. You guys didn't call me on that. That should be an E. You're gonna call me on stuff, friends. I have a V coming soon. That's why I was getting ahead of things.
What is key? Oh yeah, that was the potential.
Yeah.
Or not.
V is the potential.
That was
Yeah.
the electric.
Yeah. I was just getting ahead of myself. So what this says is that we are creating an electric field within the conductor just by virtue of moving this piece of metal through the magnetic field.
E is opposite B.
I'm just talking about magnitude. There aren't
Okay.
any vector signs, so it's okay. We're just talking about the magnitude. It's all good. Okay? We can find the potential difference. Here we go. Now we can. I was just getting excited about writing V's. We know that delta V, the potential difference, is equal to the integral of E. In your book, they talk about this in terms of the y direction, because if we're moving it this way, the separation is going to happen in the y direction. So the electric field is going to happen in the y direction, and the potential difference is going to happen in the y direction. So to be a good kid, we're going to write this in the y direction. We're going to integrate over dy from 0 to, well, it's the full length of the bar. Okay. We know that E is equal to VB. So it's going to be the integral from 0 to L of VB. Oh, wait, that's all constant, dy. So that's just a really nice, really simple integral to say that the potential difference that's created is equal to V times B times L, the length of the bar. There's my big V, little v. Yay, we did it! Now, we're going to make it a little more interesting. Because why not?
We're going to use epsilon instead of delta V.
No.
No.
You just chill out, buddy.
So it's a little bit more interesting.
I'm going to put wires here. Because now I have a potential difference, right? And so these electrons, do they want to hang out together? No. They would be very, very happy to leave. So let's, I don't know, put a light bulb here. Gentlemen, I would really appreciate if you'd stay with me. We don't have a lot of time, and I have quite a bit that I want to cover, and this is important stuff. Thanks. As this bar moves in this direction, you've got a potential difference created, but now I'm giving those electrons a way out. Right? They're not going to go back through the bar this way because there's an electric field there, but they've got a way out. What's going to happen?
Go through, light the light bulb, they're going to reach the top, and they're going to go right back to the bottom.
Nice! We got light! That's so exciting! So we can light up a light bulb with no battery. Free energy! Sweet! We've solved all of the world's problems today.
Is that all it took? Wow.
That was it! I know, wasn't that nice? Like, boom, free. I mean, like, honestly, if we could get free energy, then everything else, whatever, it'll all be good, right? What's the not trick, but what's the
R has to be
thing?
moving in the magnetic field.
The bar does have to be moving.
They're supposed to be working.
You have to have a magnetic field. You have to have something.
No, but the magnetic field is easy though if you have a magnet, right?
I mean, yeah. So we can create a magnetic field. That's not a big deal.
That's the movement that takes work. Or wait, I guess it. If we didn't have friction, yeah, but
You could make
we
it.
didn't
You
have
could say it
everything.
would
No
say-
friction!
Right.
There's no,
You move the bar, you charge a machine that moves the bar.
Okay. Let me ask a question.
No, it's that you gotta have friction and then
When I hook
you
this
can
up-
have a perpetual motion machine.
When I hook this up, this bar is moving. Yes.
Yeah.
Okay, and it's all happening. The light bulb is lighting, and life is good. That means if the light bulb is lighting, there's a what going through the light bulb? A current. What direction is the current going in? Clockwise or counterclockwise?
Clockwise.
What?
Well, technically
Oh,
it's going
yeah,
counterclockwise.
Let's talk it through. So the electrons are going which way?
Counterclockwise.
The electrons are going counterclockwise, so there's a current going in this direction. So that means that there's current going in this direction, yes? If there is current, now you've got charged particles that are moving in the upwards direction. Right? So get your right hands out again. Current's going this way, B field's going this way. The bar is going to feel a force in what direction?
That one. Opposite the.
This way. Opposite the motion of the bar. So in order to get this bar to move at a constant speed, what do you have to do?
Apply a constant.
You have to apply a force. Yes. Okay? So in order for V to be constant, we know, okay, that we're going to have an applied force that's equal to the magnetic force caused as a result of this, okay? And that FA must be applied continually. So there really isn't free energy because you're going to have to apply a force over a distance. That force over a distance implies that you are doing what to the bar? Work. So really this is just a conversion of mechanical energy into electrical energy.
What does it say is equal?
What's that?
What does it say is equal?
The applied force has to be equal to the magnetic force going backwards.
Connected, oh god.
Oh, it's so all connected. Oh, it's so all connected. Oh, yes. All right. Questions? We doing okay? Yeah? Okay. I'm going to give you a problem to work on with this. I also printed it off for you because it's not from your book. So you don't have to like copy it all down because that seems like a...
These are actually.
Can I also use the restroom?
Yes. No. One at a time.
I'm assuming you guys are not going to come work in the hallway. I have to worry about that with my like 8th graders, you know. All right. So it, as Teresa just said, it is all connected. You're going to fit all this together. I drew up here some stuff to make it a little bit easier to read. I think it should be fine. So this is just a fancier picture of what I drew. I guess they put the light bulb on the other side, but it's the same situation. So the tasks at hand are to find the induced voltage or induced EMF, okay? And then to use what you know about circuits to find the current and the power and take 2 more steps after that. So I'm going to give you a couple minutes to work on this. I want to go 1 more step after this, so I hope we can get there. Yeah, talking about the force on the bar. So that's, how do we find the force on the bar? The magnetic force is going to be,
ILD.
yep, sine theta, but the theta is 1. Did you get an answer for that?
V equals IR.
Yeah, no, so it's voltage is 0.5.
Voltage is 0.5, light distance is a half.
What's that?
It's the light.
Jesus, oh my god, yeah. Can't do math.
The sliding bar has a length of 0.5 meters.
Oh.
So 0.5 amps.
Sorry, I hope that didn't sound snarky. I was just looking for it myself. I didn't intend for it to if it did. And then for part D, the idea here is to talk about the power dissipated and figure out it based on that
Well,
how much force is applied.
isn't it looking at
It is.
Yeah.
Then why would the force just?
It will be, but you're trying to prove that it is. Yeah. So show that the force is the same. So power is work per time. So that's like force times distance over time, which is like force times velocity. Is that okay? We've done this before. We did this in chapter 5 or something like that. So knowing the velocity and knowing the power, then you can find the force applied. And as Nathan said, you should get the same. Is that going okay? Do you need another moment still? That's fine if you do. That's fine. I just want to tie this all up into a nice, neat package before we go. Are you good?
Yeah.
Okay. All right. So stay with me for another 2 minutes. I just want to make sure that this makes sense, or help it make sense. So don't turn your brains off yet. Stay with me. Don't pack up your stuff. Listen. Okay. Every time I do this, it gets a little bit funny. So we just said that we had this first experiment where we were dropping the magnet through the coil and we got an induced current, right? Magic current that comes from nowhere, and you told me that it came from this moving magnet thing going on, right? And then we talked about Faraday's experiment, and we noticed that there were some similarities, especially on this end. You told me that an induced current was caused by an induced voltage, which was caused by a what? Friends, stay with me. Wake up.
Change in magnetic field.
Change in magnetic field. So you're telling me that an induced current is caused by an induced voltage, which is caused by a change in magnetic field. My question to you is the magnetic field changing in this story? There is no changing magnetic field in this story. Do I have an induced current? Yes. And the induced current comes from an induced voltage, but there's no changing magnetic field. What's going on?
The bar is moving.
Changing like the region it's moving. So like,
Say that again?
if it's moving in each new area enters magnetic field influences, so it's changing.
Charged part of
The magnetic field is the same.
So the strength of the magnetic field is the same, but you're almost there, Andrew. So when this thing moves, the amount of magnetic field inside this changes. Are you with me there? And we're going to write that down really quickly. This is the last thing we need to do. Here we go. So this induced current
Forces
comes from an induced EMF, and that comes from either a change in magnetic field or a change in the amount of area. Stay with me, you guys. This is really important. This is the fundamental piece for all of this chapter. Change in magnetic field or the change in the area that's enclosed. And because those two things are interesting, we like to multiply them together. And we get this thing, capital Phi sub B. This is the magnetic flux. More flux. Okay? And this magnetic flux, or the magnetic flux, is defined as the area of a loop times the strength of the magnetic field that's going through that loop. Okay? So it's AB times the cosine of theta, and we'll talk about what that means next time.
Isn't it also U, I? We already have.
We've talked about flux, but it's the electric flux.
No, isn't there? How would you want to live like a line?
Yeah, that wasn't this though. This is a new content. This is a new product. All right, friends.